So let's go over what's called a precise definition of limit, or in other words, the epsilon delta definition of limit. This is the best way to really understand calculus on the deepest level possible at this level. Um, so advanced calculus will tell you a little bit more about this, but until we get there, uh, this is what we got, and this is about as good as it gets. It's awesome stuff. Not easy though, not necessarily easy. So I really need to understand it too. So pause the video and read this example, and I will start working on it. So what we need to do is we need to find how much power is needed to maintain the temperature at 200 degrees Celsius. So the temperature is 200, so I'm going to put 200 over here. It's 0.1 W squared plus 2.155 W plus 20. So what we have is we have a parabola, which I've graphed here. We have a parabola, and we're trying to see what the temperature has to be at 200. Okay, so it's somewhere in here, somewhere between 20 and 40. Okay, so notice that the parabola has a vertex that is negative. Okay, so but that's okay. Anyway, so we move the 200 over, 0.1 W squared plus 2.155 W. And then when you subtract 200 from both sides, you get minus 180 over here. Okay. And when you use a quadratic formula on this, okay, you get W to be 32.998. Keeps going a little bit. So W is about 33. Okay. So the answer to the first part is around 33. Or if you want, you can put 32.998. All right. So apparently, if we blow this up a bit, at 200, we get a little ruler out. 200, we get 33. Okay. And I'm drawing this for a reason, precisely, somewhat precisely, because, let's see, this is 246. It's a little further down than that. Hang on one second. All right, so I decided to just draw it really precisely. So this is 33 down here. It's about 33. Okay, and so when W is 33, this is W, and then the temperature is 200. Okay, so that's how you do that. Let me erase this here. Doesn't matter what's going on the other side. Now, the next part says if the temperature is allowed to vary from 200, okay, right up to plus or minus degrees Celsius, what range of wattage is allowed for the input power? All right. So what they're asking is if we're going to allow it to vary a bit, okay, on either side by 1, all right, what does the wattage have to be? So if you look, we need a little better precise graph. So what I did was in the original graph, I graphed it from negative 50 to 50 on the x-axis. So this is 50 over here, and this is negative 50 there. But I subsequently graphed it a lot more precisely from 30 to 35. So once you realize that it's at 33 is about 200, then you can make the domain a little better, a little more precise. So I'm going to draw what's going on. So that's the scenario right here. What I did was I drew, I'm sorry, this is at 201, this is 200. This is at 200, it's 201. So 201 is on top and 199 is on the bottom, okay? So that's 201 over here and 199 over here. All right, so when you take those values of the temperature, okay, the question is, what are the corresponding values in the wattage? Okay, it's the wattage over here. Okay, so the way you really figure that out, what is this wattage? The way you figure that out is you do the same thing you did before, but you're going to replace 200 with 201 and 199. Okay, So you're going to take this and replace it with 201, and you're going to take it again and you're going to replace it with 199, and then you're going to use the quadratic formula. And the answers you get are, okay, so on the left, what you get is W equals 32.884, and on the right, you get W equals 33.112. Okay, so let's see what the difference is here. So basically, you have 32.884. This gives you a temperature. So if the wattage is this, then the temperature is 199. And if the wattage is 33.112, then the temperature is 201. Now, so if you're the technician, so the technician has to must keep the wattage between these two numbers, between 32.884 and 33.112. Now, what's the difference here? So the difference between this and 33 is 0.116. And the difference between the other one and 33 is 0.112. So if someone said, well, I just want to keep it within a range that's the same on both sides, okay, you would have to pick the smaller of the two, because otherwise, if you pick the bigger one, you might fall outside the range. Okay, so and this is important with the epsilon delta definition of limit. Basically, what I'm saying is the following. Here on the left, okay, on the left, you have a difference of 0.116. And on the right, you have a difference of 0.112. So, and you can see that in the graph. These are, the left side is further away from the green than the right side. So if you want a single number on either side, number range on either side of 33, pick 0.112. Okay, if you pick 0.116, then what you're going to do is this orange dotted line, this orange line is going to be over here. It's going to be 0.116 away from 0.33, and it's going to fall outside. Sorry, this should be a dotted line, not a dotted curve. It's going to fall outside of that 201 range, okay? And you don't want that. So we're going to pick 112 as the answer there, all right? So essentially, this is what is going on with the epsilon delta definition of limit. It says the following. So let me write all this down in a different form that will be closer to what we have for epsilon delta. 0.112, 0.116. So basically, it says if, all right, so here we go. So if the temperature can range 1 on either side of 200, then the wattage can range 0.112 on either side of 33. Okay, and this is essentially application of what's called the epsilon delta definition of limit. Okay, so I'm going to write out the same problem in terms of epsilon delta. So let me go back up and I'm going to call this function, f of w, okay? Or t of w. Oh, it's called t of w already. So the question, so in terms of limits, we have the following. The limit as w goes to 33 of t of w is going to be 200, okay? So we can prove this, okay, so we can prove this the following way, as follows. Sort of. We're getting there. Okay, so I'm going to draw the graph again. Okay, so if someone hands us a range, okay, around 200, so in green is range around 200. In the previous problem, that range was 1, but it could be 5, it could be 10, whatever. Then what does the range around 33 have to be? What does the range around 33 have to be? Range around 33. In order for any temperature in that domain, in this domain, in order for any temperature to land within the range of what we have around 200. So written in words, it's the following. It says, okay, and that's the idea. So, for example, if someone hands you someone says, okay, it can be within 5 of each side, okay? So in other words, 195 and 205, then you have to determine what these numbers are here. Now, it's going to be the minimum of the two, okay? So there in red is going to be an x1 and an x2. Well, let me not use x. Let me use h1 and h2. So we're going to use the minimum of those two. Use the minimum of h1 and h2. All right. That's what we did up here with the previous problem of 0.116. Okay, 0.112. I'm sorry. Remember, we had 0.116 and we had 0.112 we could choose from. You're going to choose the minimum of those two. All right, so that's that. So let me give you the epsilon delta definition of limit to get this all started. Okay, let's draw the scenario out graphically. So you're going to be given a function. Let's draw that in blue. So suppose it's like this. Okay, now there's going to be a number that you're approaching, so let's call that a, and the limit to a is going to be L. Okay, so what we need to do is we need to prove that the limit as x goes to a of f of x is equal to L. So in blue here, this is f of x. We're going to call it f of x. Okay, so the way we do that is we pick an epsilon, and we pick a distance around L. So I'm going to draw that with horizontal lines. Now these horizontal lines are going to be the same distance away from L, okay? And with those two horizontal lines, they correspond to vertical lines. All right, let's draw those. And these vertical lines have to be equally distant away from L. So we might have to modify this a bit. Not equally distant away from L, equally distant away from A. So they don't have to be, but we want them to be. But so in the beginning, it's okay that they're not. All right. I'll modify this in a bit. So once again, the limit as x goes to a of f of x is L means that if you pick any two vertical lines, we're going to call these v1 and v2. I'm sorry, horizontal lines, h1 and h2. they correspond to vertical lines, call these V1 and V2, such that if you pick an x value in between V1 and V2, the corresponding f of x value lands between H1 and H2. Okay? And that's how it works. So if you pick these vertical lines as the same distance apart, okay, this should work for any value you choose in between them. Okay? So here's the deal. Someone could give you these two horizontal lines really, really close to L. Okay? They could be really, really close to L. Okay? Well, then the vertical lines will change. So in other words, let me draw that. So let's draw that in let's say, well, we'll use green again. Well, let's use purple. So someone could say, okay, well, what about these two? So I'm getting really, really close to L. All right, well, then there's two corresponding vertical lines that will be around A, that in which if you pick a value in between them, okay, now notice that the x is no longer in between them, so it doesn't matter, you pick a different x, maybe an x over here. So f of x will land between the horizontal lines around L. Okay, so once again, I picked two horizontal lines, this one and this one, and then they correspond to vertical lines, such that if any value you pick between the vertical lines will land, the function value will land between the horizontal lines. All right, so let me write this out. First of all, let me erase. All right, so let's see. So let me write all this out. So I'm going to keep the graph there. And let's write this out. So we're proving this. So the limit of f of x as x approaches A is L means that, all right, here we go. For any two horizontal lines H1 and H2 equidistant about L, and now the other one was in blue, there exist two vertical lines equidistant about A, equidistant about A. Okay, now the two vertical lines are V1 and V2, but V1 can't equal V2, okay? If they're equal, then they're going to be on top of A. You don't want that. The limit is not concerned with what's happening at A itself. It's concerned with what's happening around A. So if you made the vertical lines one on top of the other, okay, on top of A, then none of this would work. Okay, we're not talking about a limit then. Okay, there exist two vertical lines equidistant about A. Okay, so this is how they are, such that if x is between V1 and V2, f of x is between H1 and H2. And that's how it works. So let's look at this, all right, with another example. So here we go. Let's look at it with a graph going up like that. All right, so I'm going to choose my A, and I go up to the graph and over, and this will be L. Then I'm going to choose my horizontal lines around L, equally distant around L. And then there's corresponding vertical lines. These are blue. There we go, around A. All right. Such that if we pick an X value in between the two vertical lines, here's X, then the f of X value lands between the two horizontal lines. Now, you could be a smart aleck and say, well, I'm going to pick two horizontal lines that are even closer, okay? Well, then I pick two vertical lines that are even closer. And this just goes on and on and on. You can get as close to L as you want because there's an infinite number of numbers between your whatever horizontal line you draw and L. Okay, so let me label these H1, H2. This is H2. This is H1, and then this is V1 and V2. Now, this is still the informal definition. Let's get to the formal definition. I'm going to call the distance between H2 and H1, I'm going to call that epsilon. So I'm going to say this is epsilon. Epsilon. And I'm going to call the distance between V1 and V2, I'm going to call that delta. Now, it needs to be the same delta, so what I'll have to do is draw, I'll have to use the minimum delta possible. So the minimum V1 possible, so I'm going to have to draw a vertical line that is the minimum distance around A, okay? So that would be this one here. Delta is the same on both sides, all right? So here's what the definition is, the real definition. Okay, so the precise definition, finally we're there. It says the limit as x goes to a of f of x equals L means that, and here we go, for every epsilon greater than 0, there is a corresponding delta greater than 0, such that if 0 is less than x minus a is less than delta, then f of x minus L is less than epsilon. I do need to add one more thing though. This is absolute value of x minus a here. Okay, that's really important. Absolute value of x minus a, because a could be, the x could be on either side of a. Okay, so the absolute value of x minus a is the distance between x and a. Okay, between x and a. You go back to your algebra class and you can see that. And then the absolute value of f of x minus L, this is the distance between f of x and L. All right, f of x and L. So one way to look at that is the following. If you have 0 less than x minus a is less than delta, and this is an absolute value, then if we just forget, we can modify this for in a second, but I just want to look at this without the greater than 0. Greater than 0 just means that x can't equal a, okay? So this piece here on the left, this just means that x can't equal a. All right, so if we take that for granted, so if we take that into account, then this piece here if you go back to your algebra class, the way you look at this is negative delta less than x minus a less than delta. If you add a to both sides, all three sides, excuse me, then you're going to get a minus delta less than x less than a plus delta. And so what this means in the sense of your graph, okay, is that if you look on the left, the a minus delta, this graph is at the point a minus delta. Delta is just a number, so if it's 3, it's 3 minus, it's a minus 3, okay? That's all it is. And then this is a plus delta. So what this means is that x is between them, okay? So x is between them. All right, so what that means up here in the definition then is that it says if x, basically x is between a minus delta and a plus delta. That's what this expression means here, okay? All right, now if you take this one here, the f of x minus L less than epsilon, it's the same thing, okay? So I'm going to draw that. So L plus epsilon here and L minus epsilon there. So what this means is that the f of x that you get out of this, either one of those x's, okay? So let's just choose, I don't know, this one. That means is that f of x is going to be between L plus epsilon and L minus epsilon, okay? That's another way of writing this piece here, okay? So just study that. And that's how this works. That's the precise definition of limit, okay?